So yeah, today I will present you hit the bullseye, detecting browser exploits abusing the X memory in WebAssembly. And so hi, I'm Edward, and I performed this research with Tao. We are both security researchers from Palo Networks, and we are mainly focusing on vulnerability research on the offensive and defensive side. So today, what's the planning? First of all, we go through a quick background and introduction about our research. Then we'll dive into the V8 WebAssembly engine internals that are needed to understand our detection system. Detection system that I will present to you afterward, and I will finish with a quick demo and summary of the key points of this research. Today we are going to mainly talk about browser exploits and detection, and specifically detection of specific exploit technique. So what's this technique about? Let's see a typical attack scenario of browser exploits that is abusing the X memory in WebAssembly. So an attacker will get arbitrary read and write and address of primitives and use that by exploiting the vulnerability in the code section. Then the attacker will create a WebAssembly module and instance, and this will allocate some RWX memory into the browser process memory. Then the attacker will use its arbitrary read and write to write shellcode into that memory region. And finally, it will use a WebAssembly export function to execute the shellcode. So like I said, this is a typical attack scenario that attackers are using a lot. And how popular it is and why? So we computed some statistics of the past 3 years, and out of the 32 publicly disclosed exploits that we analyzed, 29 of them are using this technique. And why? So it's very simple to use. It's very effective and stable. Indeed, it's very exploit friendly, as it is existing RWX memory into the browser process. So it's a perfect way to bypass GP and any mitigation. In terms of mitigation, so there is a WebAssembly memory protection flag that could be easily bypassed when the attacker gets arbitrary read and write. There is also a pretty recent one, which is the V8 sandbox. This one is very efficient, but also could be bypassed. And during this talk, we are not talking about mitigation, but we're talking about detection. So we had a couple of ideas to detect those the exploits that are using these techniques, but overall, like our main goal was to protect the RWX memory. So our bullseye here is this memory. So let's now talk about the V8 WebAssembly engine internals that will help you to understand our detection system. So first of all, let's talk about the WebAssembly compilation pipeline. This pipeline is pretty complex, and also V8 engine is still in development. So there is lots of changes happening. But right now, basically, the compilation pipeline would look like this. So we would have like the startup phase where the compilation and instantiation is happening. And then we'll basically have the warm-up. So at this time, V8 is using two different compilers for WebAssembly. The first one is Liftoff, which is the baseline compiler, and the other one is Turbofan, which is the GIT compiler. V8 is using lazy compilation, which means that a function with a WebAssembly function would actually be compiled the first time it is called. So let's say, let me just show if I can. Okay, I can. See here? Yeah, perfect. So let's say there is a function call here. This function will actually not be called here, but will be first of all compiled and then be called. When this function is called multiple times, the function will become hot. So it means that the function is important. So we need to compile it using the GIT compiler. So Turbofan will compile it, and then we can just call the optimized version of it. So this is when all the compilation is happening. This is the warm-up phase, and and all the compilation is done either by liftoff or turbofan, then the system becomes stable. Now, if we take a look at from the JavaScript to the V8 internals to what is happening in memory. So on the top left here, you will have the JavaScript code execution. On the top, the bottom left, you will have the V8 internals codes, and on the right, you will see the memory. So first of all, let's say we create a module, a WebAssembly module. So it will eventually call those APIs, but the one that is important is the new native module one, because this is the one that will allocate this RWX memory region. And that native module would then generate some code in that region. So first of all, it will call the add code space locked function, and this function will generate the far gem table. This far gem table is like the name. It's a gem table, but it's basically gems that are jumping to some V8 internals function. And we'll see its usage a bit later. Also, the function add code space locked will call the initialize gem table for lazy compilation. That will itself call generate lazy compilation. And so this lazy compile table is pretty easy to understand as a structure. Like it's basically some pushes. And the push, it pushes an integer here, which is the function index. And then it jumps to this address here that is in the far gem table. And this is actually a jump to somewhere in memory. And this somewhere is here. And this pointer is actually a pointer to WASM compile lazy. So what it does actually, it's just pushing the function index and calling the WASM compile lazy function. And finally, the native module will add a main gem table. This is where basically all the export functions will point to when the export function is called from the JavaScript. So this is basically the entry to the function execution. But we'll see later how it is used. Perfect. Now that we have seen like the module creation, we'll talk about the module instantiation. So there is a couple of ways to instantiate a module, but at the end of the day, all are calling the same low-level WebAssembly engine internal function, which is instantiate to instance object. So like I said, instantiate to instance object is executed when the instance is created from the JavaScript. And this function will basically execute the instance builder that will associate the WebAssembly instance with the RWX memory region and initialize and allocate all the memory buffers and objects related to this instance. It will also process the export functions and return, one important thing also is that it returns a WebAssembly instance object. And we'll see what it looks like. Here is the class with pretty important arguments like the module associated with it, the exports also, and another interesting argument is the gem table start, as it gives us access to the start of that RWX memory region. So like I said, the instance builder is processing exports, and so it gives us access to how WebAssembly exports in JavaScript are actually what they look like into the V8 internals. So there is this function here that is WASM exported function new that is creating internal representation of the function in the V8 engine for each WebAssembly export function. And this gives us access to the shared function info and to the function data. And so the function data is one of the most important class here for exported function, as it gives us access to the wrapper code, which is a very important component, and we'll see how it is used after this slide. The instance associated with the function index, and its signature, for example. So now I just talked about the wrapper, and the wrappers are pretty important because when we actually call an export function from JavaScript that's this wrapper that is allocating and typing the parameters and the return values for the export function. It is actually compiling, computing the call target that will lead to one of the entry in the main gem table. So for example, let's say the wrapper here computed the call target finishing by 9000. It means that we will execute the entry at index 0, which will eventually jump to the lazy compile table, which will push the index of the function and jump to the WebAssembly compile lazy. So at this time, WebAssembly compile lazy will be called, and what it does, it will actually compile the WebAssembly code into the RWX memory, and at the end, it will patch the main gem table with the newly compiled code address. Now, what is happening when an export function is called multiple times in JavaScript? Most likely it will be optimized. Here, two things can happen. The first one is that the wrapper code gets optimized, so the allocation and the typing of each parameters and return values is faster. So when this happens, there is this API here, replace wrapper, that will do the job by replacing the wrapper into in the WebAssembly exported function data. And the second thing that can happen is that Turbofan optimize the baseline code. So when this happens, some newly optimized code will be compiled into that RWX memory, and also the gem table need to be patched with the newly optimized code address. So that's pretty much it for the V8 WebAssembly internals. So now we can talk about the detection system. So WASMGuard is a hook-based system for runtime detection of browser exploits that are abusing this RWX memory this RWX memory, and is based on 3 detection systems mechanisms. So the first one is detecting illegal content changes in that RWX memory region. The second one is checking the integrity of that region, and the last one is detecting shellcode in that memory region. So these mechanisms can be used independently, or they can be used together to maximize the detection efficiency. So let's talk about the first one. So let's say we have our dynamic analysis system, and we're going to input our samples. Then we're going to launch our application process, let's say Chrome, and we're going to inject our detection mechanism. So like I said, our detection mechanism is based on hooks. So the first hook we're gonna put is on the WebAssembly instance creation, and at the same time we're gonna create a WebAssembly RWX memory address and content map. So the first thing we do when we hook the instance creation, we're gonna log the current content of that RWX memory, and the second thing is that we're gonna hook the export wrapper, because the export wrapper is called when an export function is called from JavaScript, so we want to stop the execution there so we can perform our security checks. Another hook we're going to put is on memory content updates, because we want to detect when there is illegal content changes in that RWX memory. We have to know when there is legitimate changes in that region, either because there is optimization, or just recompilation of the whole module. So when we hook that, we update our map, and the last hook will be on the export wrapper replacement. So like I showed, like during the V8 internals, the export wrapper can be optimized, and so will be replaced. So we want to know when it's replaced, so we can hook the new wrapper attached to it, so we can at the end hook the export function call. So now when the export function is called from the JavaScript, our hook on the export wrapper will be triggered. And at this time, we're going to access our memory address and content map, and we're going to compare it with the current one. so we can provide a verdict. So to talk about the APIs we used for our POC, for the instance creation, we use the instantiate to instance object API. From there, we can retrieve the RWX memory address and the RWX memory content, and update our map with them. And we're going to also hook the WebAssembly exported function new, so we can get access to the code wrapper as a parameter, and its address, so we can hook it if it's not already hooked. Now for the memory content updates, we're gonna hook publish code logged and patch table jump table logged. And from those tools, we can retrieve the RWX memory address and the RWX memory content, and we can update our map with those new values. Then for the export wrapper replacements, we're gonna hook replace wrapper. Again, from the parameter, we can get access to the wrapper code, and from it, we can access to the address of the start of the code, so we can hook it if it's not already done. And finally, the JS to WebAssembly wrapper. So the one that is called actually when an export function is called from JavaScript. So from the JS function, as a parameter, we can get the RWX memory address and content and compare it with the one we logged in our map and provide a verdict. Now our second detection system, which is checking the integrity of the WebAssembly RWX memory. For this one, we kept some hook, as you can see, but we added a one which is we hooked the WebAssembly code patches into that RWX memory, and instead of creating a map of an address and content, we're just gonna create an export function map with the address of the function and their size, their code size. So when an export wrapper is triggered, we can retrieve the gem table called target, and from that called target, we can retrieve the address of the function that will be executed. So we can go into our export function map and retrieve the size of that function. So we can just extract the code and perform integrity checks on the code. After that, we can provide our verdict. So for the hook on the WebAssembly code patches, we are hooking publish code locked. From there, we can retrieve from the WASM code that is as a parameter, we can retrieve the function address and size and export our export function map. Now, when an export function is called from the JavaScript, our wrapper hook will be triggered. From there, we can retrieve the function called target, and from the function called target, the gem table entry. So our first check here is checking the integrity of that gem table entry. If the check passes, we go and retrieve the function address, check if that function address is in our export function map, and then our function size, so we can retrieve the code and perform our integrity checks on that code. Now, for the checks, for the integrity checks, first we are going to see what are the integrity checks when the function is called for the first time. So, like I said, V8 is using lazy compilation. So, for the first call, we can first check that we can check the integrity of the gem table. So, checking the jump instruction and checking that the address we are jumping to is actually in the lazy compile table. Then in the lazy compile table, same, we can check the integrity of the instruction and check that the address to jump to is pointing to the far jump table, and that far jump table is actually going to call the WASM compile lazy function. Now for the function compiled with the baseline compiler, which is liftoff, we can check the prolog. So that would be the first check we do. Then we can check the internal structures access. So for example, here RSI would always be the WebAssembly instance object, and from that object, some arguments are accessed, like the stack limit address or the chain budget array. So we can check if those access are done. And finally, we can check the VH internal function calls. So for example, here we have a jump that is that will be actually jumping to the file jump table and executing a WebAssembly stack guard for a stack check. And there is a couple of examples also that are done. And we can also check the epilogue that I didn't include it into that in slide. So yeah. Now for checking the integrity of turbofan compiled code, that's where it can be tricky. So first of all, we'll try to apply the same logic as the one we use for liftoff. But the thing with turbofan is that it's an optimizer, so it can get rid of the prolog, the structures access, the internal function calls. But it doesn't really happen in the exploits we analyzed because it can bring some instability to the exploit. But if it's done, we are just going to compute the function content hash and ensure the integrity like that. We'll just put some example of turbofan compiled function. So here on the left, it's the baseline compiler liftoff, and it will compile it into turbofan. As you can see, we get rid of all the internal structures and the jump to the file jump tables. And now for our last system, so we still hook the instance creation, the export wrapper replacement, and the export wrapper calls. But at the end, when the export function is called, we're going to retrieve the gem table called target and execute the WebAssembly compile code using shellmon and shellemu. So both, I'm going to explain what are those two systems, but one is for monitoring and the other one is for emulation. And from there, we can retrieve some verdict. Yeah, just for the logic of when the export wrapper is called. From there, we can retrieve the function called target, and from the function called target, the RWX memory address and size, and then we can retrieve the code and input that code to shellmon and shellemu. So shellmon is a shellcode detection system that is taking as an input some piece of code and executing it into memory and monitoring its behavior. So it's basically just kind of tracing some sensible Windows API calls. And shellemu does kind of the same thing, but using emulation. And for that, we are using chilling emulation engine. And one feature, an additional feature is the ISM level detection, where we can check the access to TEB, PEB, structures access, DLL accesses, and some also famous shellcode technique like getPC or self-decoding. Now I will go through the demo real quick. Okay. So for the demo, I will use the CVE 2022 4174 exploit. So the actual bug and the exploit were presented at Black Hat US of this year. So if you want to know more about it, you can just check the talk. So just to explain a bit like what's the setup here, we have our command line shell here. Here will be the Chrome process, and then just like the Chrome process PIDs right there. So the first thing I will do is just execute some benign one. I'll try to speed up a bit. Yeah, so at the end I will just show a bit the code of the exploit. Like I said, I will not go through it, but you can check it out in the Black Hat talk. I just want to show like the usage of the WebAssembly module and instance and the export function here. The fact that also they use arbitrary write to write the shellcode and then execute the export function. So when we execute it, we'll see some calc.exe pop-up here. So let's talk about our first detection system here, mechanism. So what I will do is we would inject our detection mechanism into the Chrome process. Let me see if I can. I will execute some benign one to see if that we don't have any FP. And at the end, I will execute I will execute the exploit, and right now it's just a message box for the demo purposes, but we can see that we detected the exploit. For the second one, we'll have the same setup, same output also. So we'll inject, call some benign one, and finally call the exploit, and we'll see that we detected it. And for the last detection mechanism with Shellmon and Shellmu, I will start off by Shellmon. Shellmon and Shellmu are outputting some logs right now. That's our way to do it. So pretty much the same scenario. I will inject our detection mechanism right there, and then execute the exploit. And let me see the logs. Yeah, here. So here you can see the logs with the call, for example, to the create user process with the call.exe string. And the last one is the Shellmu detection. For this one, same thing. We're gonna inject. Let me just show you the output of this one. So this one gives us more information, I guess, because we can trace the access to the internal structures. So for example, here we have a PB access, some kernel-based.dll accesses, a call to load library. So yeah, that's pretty much how Shellmu is outputting our results. All right. I think that's pretty much it. So yeah, we have like 3 exploitation detection mechanisms that are focusing on this RWX memory that is allocated by WebAssembly. And also the ideas could work also for other RWX memory that are used to bypass DEP and NX mitigation. And we think also that more work could be done on that, like on the detection of a specific exploit technique. So yeah, that was pretty much it. Thank you for listening.